This meeting was held in exciting Las Vegas, Nevada from July 9th through the 11th, 1999. This is videotape number 33, IPv6. Who, what, when, where, how, why.
Is running out of space, and because it comes down to the Goldilocks problem of Class C being too small and Class A being too big and Class B being just right, and they try to aggregating like sticking together blocks of Class C and then have the router route it together, classless interdomain routing. But that's only a temporary fix because our routing tables are getting smaller. Yeah? IPv5, yes, actually that's, I think on the next page. Yeah, it's on the next page. Yes, there was. IPv5 was actually it's in use, it's a stream transport protocol made by the IETF, the Internet Engineering Task Force. That's what makes most of the protocols. But IPv5 is out there, so they called it IPv6. Actually, competing proposals were IPv7, 8, and 9, and so I don't know what the next one will be, but they had, the routing tables were getting too big and too complex to try to route all these things because everybody wanted a Class B address. We have more than 256 machines, we want a Class B address. So we need, the other thing, why do we need a new version of the protocol is we need address renumbering. They decided, the IETF and some other people were figuring that we needed address renumbering. Whenever we moved from one provider to another, we'd have to renumber all of our addresses, and nobody wanted to do that manually anymore. In the original days, it was all set up, the routing tables was just manually entered into the computer in the Unix boxes. But the mobility of the computers, and the computers are switching from one to another. I mean, my Palm Pilot has an IPv4 stack. You know, everything is getting more and more connected to the internet, your dishwasher, you know, your microwaves on the internet. But they decided that they needed more and more stuff and to renumber the addresses. We needed to get real-time traffic because in order to get real-time traffic, say I wanted to get video on demand, I could just go and start watching Terminator 2 over the internet, and I want it not to lag every time. I mean, real audio and real video is bad enough. We needed some auto configuration, meaning that we wanted to be able to take a computer out of the box, plug it in the wall, and have it automatically figure out where it is, who its neighbors are, where its routers are, the nearest router, etc. And of course, why we're all here is they needed more security. Currently right now, IPsec or IP security, which is about the last half of the talk here, is on IP security in general. They needed to add that in, so they put it as a mandatory feature. So what is it? As I said, it's a complete overhaul. They didn't just extend it. They completely redid the headers. They're working on TCP/v6, etc. Started in 1992 through the IETF process. Other protocols were developed. Proposals were sent out. You know, the standard protocol development of IETF.org. They wanted to have a larger address space, obviously because of this, because they wanted to be able to waste some space in order to make our routing tables easier. So they didn't, right now you've got to have everything just right on the classes, and they wanted to make sure the mobility, they've got mobile IP for v6. The different traffic classes, FTP, email, bulk versus, for example, like real-time video. They wanted to make sure security, or at least authentication, was part of everything available. But you wanted to make sure that IPv4, there wasn't a day in which, all right, at once, we're going to all convert over to IPv6. You can't have that. So we got to have some way to transition, and I'll talk about transitioning. Okay, addresses. No longer the 128.173.1.5. We now have, instead of 32-bit addresses, we're now going to 128-bit addresses. Ooh. 8 16-bit groups separated by colons. So that is a fully qualified internet address with, well, obviously made up, but that's how long these addresses are going to be. What's that, what? In binary? 1111111100. Okay, So you need to have shortcuts, so they were able, like if you have a bunch of zeros, you could squish it and drop off some of the leading zeros and have double colons and other such like that. But for the most part, people don't need to know where addresses are. I mean, unless you're doing promiscuous mode and want to find out who's doing what, but they wanted to put more emphasis on the domain name servers, which are also going to be changed because you can't have, and that'll be discussed later, you can't just have a record, address resource record. Okay, so some hosts can have more than one interface. Before, it's like I have an IP address, there's my box. I have another IP address, here's my other box. Now, mobility can be, we can have a box connected to multiple providers. We can have a site that's connected to MCI and Sprint, so when Sprint goes down, MCI can take over without having to renumber stuff. We can add mobility, so if I move from Virginia out to here, it's automatically renumbered and I don't have to try to retype in the thing. In fact, even on campus, moving from one building to another, moving from one subnet to another requires a renumbering manually, going through and even rebooting the machine if it's Windows sometimes. Yeah. But boundaries are no longer fixed. We have what we call prefixes. So you see right there, the 3FFE 0900 : and then a bunch of zeros out, /24. And that means the first 24 bits, or 3FFE 09, is the prefix, kind of like your subnet address. But that's, and I'll show a picture of how the routing will actually work. Since the addresses can be renumbered, everybody has a lifetime of addresses. There's an address, how long it's valid for, and how long it's preferred for, so that addresses can be renumbered if, for whatever reason. So about 136 years maximum, or infinity, and you renumber it a preferred address time before the new one is sought. But they'll have different ones so that you'll know when to renumber. Now, you'll need to know that they've been divided up into a couple of categories. So why did they choose 128 bits and not, say, 64 bits? Because right now it's 32, we just numbered. I mean, 2 to the 64 is an astronomical number. In fact, 2 to the 28, I think, is about 6.7 times 10 to the 23rd addresses per square meter of the Earth's surface. That's a lot. I mean, if you heard Bruce's talk yesterday, 2 to the 128 is, almost uncountable. So why would we need 6.7 times 10 to the 23rd addresses per square meter? Because of routing inefficiencies. It's more effective to have the route wasting blocks of addresses in order to get our router tables easier and faster. So let me show you how they calculated 128 bits. Okay, so this is the only formula in the talk, but Dr. Christian Hutima, who is a highly respected member of the IETF and the IESG, the Internet Engineering Steering Group, developed this H number, and he said the log of the number of addresses over the number of bits is your percent efficiency. So if we have 10 bits in 1,024 hosts, about 0.30 if you take the log of 1024 and divide it by 10. This should be right. I want to make sure. So they've estimated it by looking at large networks in IPv4 right now, the way it is, that H is between 0.22 and 0.26. Well, if H is 0.22 to 0.26 and only 32 bits in IPv4, somewhere between 11 and 208 million hosts, if we had the perfect efficiency. Now, what they want to do is they want to connect everybody around the world to IP. They want to have a computer for every person on the planet. Soon we'll be at 10 billion people, in each of those. Up to 100,000 computers if they wanted to have, with their everything else on there. And who knows, there's objects that aren't with people. So they calculated that out somewhere between 57 and 68 bits. So instead of limiting themselves to 64 bits, they went to 128 bits. So, let me explain some new concepts to you. Unicast we've seen, that's from 1 to 1, uni being 1. It goes from one interface to another. It's a standard addressing that we use right now. Multicast we've seen right now, that's 1 to multiple interfaces. This is a class D address in IPv4. There is no broadcast anymore in IPv6 when it comes around, but they developed Anycast. So if I'm sitting at my site in Kansas, I want to find out where the nearest machine is to a group of similar machines. So if I want to find where CNN is, CNN may have a site in Atlanta and London and Moscow, but my computer needs to know where the nearest one is. So what it does is it just searches out through the router table a ring at a time until it finds the nearest server. And it's a new feature in IPv6 called Anycast. So basically any machine within a certain group of machines will be found. Let's talk about some link local, site local, and global addresses, and then I'll actually show you in the next couple slides what an address, how it will be broken up. So link local, all machines on, if I just had an Ethernet segment and I wanted to have all the machines on there, that would be called link local machines. They're not connected to the internet. They're kind of like your 10.0.0.0 machines for the Class A and other ones. You just set it out of the box and away it goes. They have site local, obviously global, but they have site local where you'd have different addresses for a group of machines that are just called site. Now what's a site? Is it a single campus or is it a company that's spread out over the world and call it a site? So there's different addresses that are laid out. And the next slide, let me show you the different percentage of addresses. And you can see the inefficiency and for future expansion. Because right now, the way they've allocated it, global unicast, which is from 1 to 1 through the global, is 1/8 of the address space. That's it. And that's one of the biggest chunks. The other biggest chunk is geographic-based unicast, which is based off of GPS or any other kind of address that's based on where the machine is. They got things in here for IPX, multicast addresses, link local, which is what I said on a particular link, site local, and others. That accounts for about 30% of the address space. And that includes every single global unicast. So another 70% of addresses is not assigned. So theoretically, you could branch this off into space at some point and maybe have IP on other planets or the moon and stuff like that, and they'll still work. Out there. So let me show you what the global unicast address is kind of like the common one, which is what most people use. I took 128 bits and divided it up into, there's the 3-bit, well I didn't, but the IETF divided into format prefix, which is those 3 bits on the left down there, which kind of tells whether it's a global-based machine or an IPX, something like that. You got TLAs, NLAs, SLAs, and the interface ID. Now the TLA is kind of like the overall global providers, while the NLA is for particular sites. So like a TLA would be something like Sprint, and an NLA aggregator, that's the top level aggregator, next level aggregator, and site level aggregator. The next level aggregator could be university, and then each university can, instead of giving out little subnets of 256 or 1024 bits each university is given a fixed format prefix, a fixed TLA, and a fixed NLA, so that each university can give out SLAs any way they want to. Well, that's 16 bits right in there that they can give out per network, so up to 65,000 networks per every site. Now, the interface ID is you take the Ethernet card and you run through some IEEE shifting around. You basically take your MAC address, split it apart, put some stuff, put a couple bits in the middle, FFFE and zeros in there, flip a couple bits, and you'll come up with your interface address. So that's how your addresses are calculated, basically off of your MAC address, since most people now have Ethernet. But if not, there's other ways of getting the 64-bit. So the 64 bits just for a machine, much less in the site and all that. Let me show you now the header. Our old IP header is gone. They still have the version number where it's supposed to be, but now they've got some different things in there. We have flows and priorities and class. Priority used to be class, and flow label. That's like saying every frame of Terminator 2 will have a unique flow label. So you can know like what frame is coming through, and you'll know that this is a Terminator 2 film that's going to this address, needs real-time video, so that the routers can go through there, see the header, figure out that it's real-time traffic, not even have to look at the whole packet and send it on. So just with a few bits, and everything is fixed. You can notice that there's no IP options anymore. And I'll cover how those are covered, but there's no IP options. It's a way that they just stick it all in there. Payload length, you can have up to 64K in a packet. However, there's ways of getting more in there. Next header is kind of like in the IP, it says, here the next header is TCP. Hop limit is not time to live, because hop limit is you decrement one every time you go through a router, because you used to have time to live, and no longer are routers every router takes less than a second. No router takes 3 seconds. Because TTL used to be the number of seconds that it was at a router. And there's your source and destination bits. But let me show you Yep, there you go. Payload length is 16 bits, but if you put the length to 0, you can have something called a jumbogram. 4 gigabyte packets. Oh yeah. Now, because over fiber and whether it's going toward that, it makes more efficiency to send larger packets. So they allow for jumbograms. The minimum MTU is 1280 bytes, and but they haven't really addressed this. But I'm not really sure what a ping of death would be with a jumbogram of 4 gig. That would be something. I don't know whether it's just like, well, it's coming, and that's the kind of vision they see. But from a security point of view, I'm kind of wondering, well, it's legal to send a 4 gig packet, but that's a serious mail bomb or a packet bomb. Yeah, don't drop those packets. And type of header, there's different, instead of using options, they've got headers for authentication and ESP and stuff like that, fragment and destination, so that every packet doesn't have to be looked at until the end. They can just, if they want a hop-by-hop header, they could, but for instance, using a fixed size header without the options and no fragmentation. If you need fragmentation, you stick a fragment header. There's no fragmentation, you allow it, but for the most part, they won't have it, so you don't have to look at the fragmentation. So the routers will be at least 40% faster with just a fixed size header in experiments that have been done. Header chaining, you've seen this, you stick an IPv4 and then a TCP and away you go. IPv6 will stick, next header is routing, the router header will say it's TCP, or the next header is routing, which will then say it's a fragment, the next thing is a fragment will say authentication, next thing is ESP, and you just chain the headers straight on down. This is ripped out of RFC 1883. Let me show you about routing. In routing, you have, if I'm at router X, we have variable length subnet masks. So now, it's your classes are A, B, and C, and everything is kind of laid out. Your routers are laid out with, they find the longest prefix. So remember that /24, what that means? That means that the first 24 bits of the 128 bits is your prefix header. So it's going to say prefix 1 in router 1, router 2, router 3, and router 4. Here's 2 examples on the bottom. If I have an IPv6 address, 3FFE 900, 111, 269, whatever else, what happens, as you can see with the bold, is it will take the router will say, well, here, let me show you over here. It'll go there to 24 bits, because it sees, it matches the first as many bits as it can, and then sends it to 1. Whereas this one, that router 1 would be matched, but so would router 4, because it's up to 100. Because these 64 bits are matched, so it'll send it to 4. For those who didn't hear, that the router 1 will be taken because it matches only up to the 24 bits, and so the longer the way down the chain, the more easy it'll be to get to the router, so that the longer addresses will go there. And that's what's called variable length subnet masks. So any network can have any number of, you could have a /24, /25 for any number of bits. So you can see how your networks can be completely aggregated or stuck together. Mobility, one of my favorite topics, the ability to move from one to another. We've got Mobile IPv6, which is IP for mobility. They've actually got mobile IPv4. They've done experiments on it. They've got mobile ad hoc networks where a bunch of us get together with our laptops and turn them on, and with infrared wireless links, we now have a system set up to play whatever game we're playing just by turning it on. The computer should be able to, that's what they want to do, you should be able to turn it on and have everybody see who's out there and go from there. But not just in a room, but anywhere. So if there is a router port or a network access point in the corner, I should be able to turn on my machine. It should be able to say, wait, there's a wireless link in the corner. My IP address is this, my nearest router is this, and automatically configure the computer to go with that. My concern is, while I went to an IETF meeting in Washington, D.C. once, and they kind of like, well, we'll put off security toward later. And that's what really concerns me, is these same attacks have been coming over and over, and you know that this is going to be a problem. But for mobility, they've got address space now to move around. You don't have to keep just one IP address. You could have any number of IP addresses, and anything can be on the internet now. Co-located means that it's going to another place through agents. Neighbor discovery is what I talked about there, about being able to just turn it on, figure out what the prefix is, what the MTU, minimum transfer unit is, or maximum transfer unit, figure out the hop length. Duplicate address detection, is my box already out there? Does somebody already have my IP number or not? And stuff like that. I've kind of answered the questions of what it is, and now trying to figure out, well, who's using it? I like my IPv4, I don't care. But, right now it is in universities, it is in research institutions. People are starting to come around to testing this out. And I'll go through later what the mechanism is, how you're going to transfer over, what the plan is. There are IPv6 stacks out there for Unix, and Windows 2000 they had said at one point they wanted, does anybody know whether they'll be in there or not?
Looks like it's
No, I don't know, but they're trying to establish it in there. In fact, one of the ways to get transition is to use dual IP stacks. But that's on the next slide. So there's a couple ways. How would we transfer this over? How would it work? Well, there's the 6-bone, which is similar to the M-bone, the multicast backbone. If you hop on and you want to see NASA's space shuttle downlink, you can get an address on the M-bone and go through that. But they've got different islands of IPv6. University A has an IPv6 network, University B has an IPv6 network, and they want to talk to each other over the global IPv4, so they use, through the IPv4C, they connect it through gateways, which translate IPv6 to IPv4, unwraps the packets and packs it back up and sends it across. You can either have dual stacks, which are one machine, you have two different stacks to handle the packets. If an IPv4 packet comes in, it knows that. If it's an IPv6 packet, it goes with that. Or you could have tunneling, which they place one packet inside of another. Just like you encapsulate the TCP inside of an IP, you encapsulate an IPv4 packet inside of an IPv6 packet. This can be done, but it's inefficient because now if the only way I can reach the other IPv6 is through these sets of tunnels, where it may just be the machine right next door, and I may have to go all the way around the internet to find my next door machine. It's inefficient, but they're trying to put it together. Okay, well that's a general overview of IPv6, and I'll come into more detail later. But let's switch gears here and talk about DEFCON's about security for IP. Now, IP security, some haven't heard of it, IPsec, they've got different headers, you have an authentication header and an encapsulating security payload. Actually, this will work for IPv4 as well. But for IPv6, authentication is required for every transaction, except when you put in like a null authentication, which I didn't figure that one out. But they put security associations and tells which, this machine is using DES to talk to this connection. This machine, we're using IDEA to talk to this machine. And Bellevin wrote a paper a couple years ago, which goes through, and they fixed a lot of the problems that he mentions, but problem areas for the IP security protocols and the reference is in the back. but the IETF had IPsec working on it, RFC 1825, 1826, and 1827. Various crypto techniques to put it in there. You can use, the reason why they have, you may ask, why didn't they just have a crypto header? The reason why is because when they developed this, some countries would allow authentication. You know, I am really Dr. Byte coming from Las Vegas. They wouldn't allow encryption through their country. So you could have it so that people could just use authentication, or you could use authentication and encryption, or you could just use encryption. But that's why, the selected use of it. A little bit about the authentication header, go read Atkinson's RFC. Basically, a base level is MD5, but you can add other stuff in there. They've got, for those security associations, you could say, well, I'm using, this type of authentication protocol, or even a new protocol has been developed, and you just stick it right in there. I'll show you the header format in a later slide. DES is the CBC, is the ESP-based thing, but we can stick in any other kind of encryption on there. So this is the header format ripped out of the RFC, where everything is based off of header chaining. The next header is this, that, and the other. There's a listing, well, it was through IANA, the Internet Assigned Number Authority, but now it's gone up. Postel has passed away, so they shifted it over to somebody else. But there's different things, the length of the header, the different types of authentication. Your index is basically a 32-bit number as to, like, this machine, you can have up to, I guess, 4 billion connections that says, connection number 1 has got this type of authentication header, so it knows which connection is going to which machines. That's one thing, host-based authentication versus user-based authentication. If I have a host-based authentication where my machines are talking to each other, then there's lots of attacks you can do, and Belvin describes those in his paper. Dr. Belvin describes how you can, if you're using the same key for everybody on the same host, then there's attacks that can be done. But for the most part, that's the AH or authentication header, which is used in anything. It's coming along. Our ESP, or encapsulating security payload, is done with just another security association and just various sets of data in here that may have keys and other such stuff. I have a feeling I forgot to put in the next header chain, but for the most part, that's that. So what is this security association that I keep talking about? The security association is, what kind of security are we going to have for this connection? Let's make like a record or a structure or whatever else you want to call it, an aggregate of different data that says what security we're going to use, what authentication method, what authentication keys, which encryption method are we going to use, and which encryption keys are we going to use, initialization vectors on various crypto, how long the key should last, etc. And there's an index into the database of different security associations that determine which things are in there through a table lookup. And you can use different ones for different connections and different machines and different sessions and other such stuff like that. Belvin, here's some of there's 2 slides of, I summarized Belvin's paper, which was a great paper where he listed, the ESP provides confidentiality, and the authentication provides authentication integrity and non-repudiation. Like I didn't send that stock certificate. No, it's failures. We need to have. He pointed out there was failures. You could have encryption broken, you could have spoofing attacks, you could read encrypted data, because if you send a telnet session is 1 character at a time, so you encapsulate one character in a packet, so if if it's the same host key, if everybody's using the same keys, go back and forth with different initialization vectors. He shows fragmentation attacks. If you haven't read Tom Patak's paper on evasion and insertion attacks. I think it's through NAI. Firewalls can be brought around through fragmentation attack. We can use fragmentation attack and ruin about everything. Session hijacking, all these problems. I mean, IPsec is supposed to solve all these, but there's still plenty of thing out there. But for defense, let's see how we're going to help solve some of this. We want to have, you don't want to have just encryption without integrity, because you can change anything in there and read it. You want to have per user, you want to have different keys per that. You don't want to have, you want just a general overall attack that people use sometimes. They'll send them a plain text and they'll encrypt something back, like give an error message, or you'll send something in ciphertext and they'll send it back in they'll send an error message in plain text. You want to have, because then that helps you with the cryptanalysis, which is not my expertise, but plain text to plain text and ciphertext to ciphertext. That's what you want to do. DNS, I'll talk about DNS later, because that's going to have to be changed with all this. It'll have to be added on. No longer will you be able to send an IP address and get back a 32-bit number. DNS security, there's a separate working group, DNSSEC, on that, where your DNS stuff will be that. And that's some neat stuff to be able to try to hose your DNS servers. Okay, so in summary, for IPsec, that is, we have the IETF has standards coming out. IPsec has been around. You can do that. You can split the headers for restricted countries, like I was saying, if you just want authentication. When I went to IETF, it's a catch-all for all other things. We'll just stick IPsec on there, or we'll figure out security later. Let me just design a protocol, a routing protocol, or a mobile protocol. And that would work, but we're sticking security on as an afterthought, and you can't do that. You cannot stick security on as an afterthought. You've got to build it in. When the internet was developed, security was an afterthought, and look where that's leading us. So they're trying to say authentication header for everything, go with that. There's the key distribution protocols. How do we do key exchanges? If everybody's doing authentication, now there's keys flying everywhere. If there's keys flying everywhere, how do you distribute this through 128 bits and many places out there? These problems some have been fixed, but every new protocol is going to have problems, and they'll come out with it at some point. All right, by where? IPv6, where's the support? Where's the beef here? We're now having a new resource record in DNS. If you're not familiar with DNS, there's A records for addresses and HINFO and other such stuff. Go read the RFC. But they're going to return quad A records for 128 bits because their addresses are now 4 times as long. And for reverse lookup, that's how you get the name from the number. IP6.int domain classes. There are different domain classes to go backwards. It's kind of the same thing we did, but the new domain class. DNS, I said something about renumbering, where if I go from there to here, from the East Coast to the West Coast, I get a new IP number. DNS needs to know now where my new number is, so that if anybody wants to send me addresses, if I have a mail server set up, it needs to know where to send it. So DNS needs to know where the new renumbering is, and DNS needs to be renumbered. So they're working on DNS. There's the IPNG working group is in the IETF, and they've set out all these RFCs. And if you go to IETF.org and look through them, that's actually where the internet, if anybody doesn't realize, that's where the internet protocols are developed. That people from all over get together and they get in working groups. It's a volunteer organization. And if you're interested in a certain protocol, you follow their mailing list. They have discussions, and they have meetings about 3 times a year, and they discuss these protocols. And if rough working code and rough consensus is, they try to get the code work 2 different implementations, And that's how protocols are developed. That's how the new IPv6 is going to be developed. So if you have any problems with protocols or want to get involved in it, just go to ietf.org and check it out. But people are putting it into place. Site operators are putting it into place at different universities. They've got IPv6 network within the university, so you're able to tack in and have islands. And it's starting to come around. It's a very flexible protocol, but things still need to come around. There's still problems out there. Well, what happens if we have a socket and all of a sudden the machine changes addresses? Well, that's a problem. The address renumbering, hopefully it will be able, that's why you have, it's kind of like when they first created stoplights, they had red and green, and that was it. And so you'd go and all of a sudden, boom, it would turn red, and people would have tons of accidents. So they said, well, we should have a yellow light so we could, have that kind of the tri-level buffer. So the same kind of thing here with the preferred length of how long it's going to be around versus valid. So I'm past the time. This thing is going to renumber soon. I need to renumber soon. Here's another problem. One of those colons, if you ever do different addresses in the HTTP, then you go, well, here's my, CNN.com port 1026 for a new protocol in there or a new page or whatever. How does it know where to parse it? So they're still working on stuff like that. So there's plenty of, because right there I intended the address to be 3FFE 2800.0.0.0.0 all the way down to A and port 8080. But yeah, you could probably pick the last colon, but then if you went to the last colon, then if the address like that was supposed to be 3FFE 2800.0.0.A colon 8080, then it wouldn't be able to tell which it is. Huh? Differentiating character. I don't know how they're solving that, but that's just a general problems, and they're still working on stuff.
For some reason they switched the colon. Did they just keep a dot or?
I have no idea. People decided that they wanted colons, I guess, in the IETF, and they went with that. I don't know. Yeah, it could be. Just different ways of addressing, and I don't know why they did that, but that's the way it's done with different addresses. The MAC address is also colons. Well, the MAC address, you actually just take it and they split it apart and stick it in there. And the MAC has colons, but it's like six different sections of 8 bits each, 6 different bytes, and they flip that apart. I don't know whether they did that or not, or whether they like colons, or whether they're going to change it to a different separator, put semicolons or backslashes or whatever. Why didn't we just why did MS-DOS put backslashes instead of slashes? We'll come around to figuring out a way to get around these things. But there's still problems that are still out there. But when is it coming? People ask me, it's like, well, IPv6 will never make it because there's IPv4 and none of the NOCs will want to switch, and none of the ISPs will want to switch. But when whatever the new IANA is says, sorry, you can't get any more IP addresses, deal with it, and people want more servers, and they start putting everything on the internet, from the Palm Pilots to your microwaves to the dishwashers, that you're going to run out of addresses, and something is going to break soon. Yeah.
So network address translation alleviated a lot of that problem.
Network address translating for those is the ability to stick a box on your site and say, okay, coming in here, this looks like one big machine. When you come in, it switches the addresses and figures out, well, actually it's going to the mail server here, or it's going to this one right here. And when you call out, the NAT knows that box A in this site is talking to somewhere over here. So when it comes back in, it knows the same session of the packet and knows to go back to A versus B versus C. Yes, that's doable, and that's one of the midterm solutions. But first of all, if you have a site, you're now creating a bottleneck unless you stick multiple NATs. If you stick multiple NATs, and there's a problem of which side it comes in and how do you route it back, so you start getting bottlenecks into the NATs, and so that becomes a problem. I've read a few papers, did a report on NATs last year. They're neat, and they're, because if you're only given one IP address, you can try to make that out, but, it's a temporary solution, yeah. Sometimes it does. Yeah, I mean, it's a temporary hack, but it's not going to be a long-term solution. Yeah. Okay, the questions was, should I download IPv6 now and play with it? And the second question was, is it going to be compatible with anonymous service like Freedom? You could probably play with it now through dual stacks. I think Linux has got one, and they've started to put in different types of stacks. Yeah, play with it. You might want to do that. I'm not sure whether, I'm not familiar. I haven't played around with the Freedom sites, but they may be, they may not. I'm not sure. But they've got it here now, but people are like, well, I'm not going to change, I'm not going to write an IPv6 stack for my VAX, which is sitting on the internet right now. And so IPv4 will eventually, IPv4 will always be around. There will always be legacy systems. That's why Microsoft Windows is so lousy, because they have to keep taking in everything from the past. It's why Intel architectures have to carry baggage from 1978 when they created the first stuff, and they just kind of keep adding it on. Backwards compatibility. That's the mantra for the computing world, is backwards compatibility. So I don't think IPv4 is not going to go away. But they want to try to shift it over to IPv6 as a primary, so then IPv4 will be using these gateways and tunnels, and it will be slower, but it will still be useful. And then there's different addresses, which I didn't go in here, but there's ways of putting addresses like, FFFF, in the address in front of your IPv4 in order to make it an IPv6 address, and other stuff like that, which you're using to kind of transform it over, so that eventually you can get an IPv6 address. I mean, I've had IPv6 addresses for boxes and IPv4, so, yeah. Sorry, yeah, you next. Go ahead.
This may be an implementation-specific question, but do you know whether network address translation or IP masquerading in a Linux box would be able to translate an IPv6 address to an IPv4 network or vice versa?
The question is whether a NAT or IP masquerading on Linux or a NAT box is able to convert one address to another. I've played a little bit around with it, but I don't know. I don't know the answer to that question.
Technically, there should be no problem.
Technically, there should be yeah, I mean, you can code it. Well, you can convert it over. You can write the stuff to convert it, as long as you know, because you got to have the right headers and the right addresses. You probably could, but I don't know. I was like, yeah. Oh, okay. With Linux and BSD, OpenBSD, you can do it. So it's coming, it's out there, and because people wonder when IPv4 is going to run out of addresses. I mean, about 4.2 billion addresses, and obviously you can't have perfect, because if you have a Class A network, if you don't have 16.7 computers, but only even 8 million computers on a Class A network, then another 8 million addresses is wasted. And you keep doing that, and the internet is going to be broken up into different chunks. So they estimate somewhere between 2005 and 2015, this was like a year or two ago, by plotting out the curves and figuring out about when it'll cross over. So there's some time. I mean, you're not going to go out, you're not going to lose IPv4 tomorrow. This is kind of like the future. When is it coming? Talk of whatever. But like with CIDR, the classes under domain routing, you got to manually renumber your addresses. But now more and more are coming onto this thing. Yeah.
I have a question on this one. Like on the local checkpoint, my organization doing matting, we have about 40,000 loads of matting. It's very practical. But my question is, what role was part of these things?
Address resolution protocol?
Yeah.
Okay, the question was, his company's done like 30,000 machine boxes on a NAT, and it works fairly well. All right, okay, it works better than fairly well. And that at what point does ARP play into this address resolution protocol? Obviously, with an IP, in ARP, you give it an IP and you say, here's this IP address, what's the MAC address, is how ARP works. In RARP, the reverse address protocol, here's a MAC address, and try to find an ARP. That's how you find, that's how diskless workstations boot up and stuff like that. Yeah, it'll probably have to be changed with IPv4. There's probably an ARP v6. I just haven't messed around with it. Yeah, well, yes, it will, and you probably could find, yeah, that's probably why they did it, but you take the MAC address is theoretically in there, but some people don't have Ethernet. I mean, Token Ring is still out there, and other such new, type. Token Ring is what? Okay, Token Ring has a MAC address, but is it the same? It's reverse order. I don't know. Different types of physical layers and data link layers, they may have to be converted, they may not. I mean, we could develop a new one tomorrow. Yeah?
Are they handling the issuing of these numbers? Is there going to be a V6 internet, or where are you going to get your legitimate V6 address from?
The question is, where do I get an IPv6 address from? Is there a NIC that I can go to and get an IPv6 address? The University, Virginia Tech had a section. They were on the 6bone. You can, I don't think I have an address. Maybe 6bone.net is what was out there, and they would allocate you a set of test addresses even now that you can hook up and try to play with. And basically, the 6bone right now is like ping, or it was like the last year or two. Can I ping this guy over here? Can I get through the routers? Can we run router tests? Can we do real-time video over this? Do we need to change this and stuff like that? So I would 6bone.net or try to find ietf.org and try to see where that goes to. Yeah. The question is, if you have a toaster and a dishwasher and everything else to the internet, how do you think the ISPs will give you a block of addresses? Is that the question? Or a network? Probably what they'll do is they may actually give you you could probably request, with the different number of networks. I mean, an ISP, if you just give them a site level address, and that thing which I put up there is just one particular format. They could say, you're within this southeast region ISP, so we're going to go through and use geographic-based addresses, and here's your chunk of your house is on this GPS location, so, everything is going to be on this. I mean, they could do, who knows what they could do, but there's different, they could aggregate it out. The whole point of using larger and larger addresses is so they could have router inefficiency. So yeah, they could probably give you 1,000 addresses and not really, care. Yeah.
The intent is that the ISP sets up the first 64 bits however it needs to, like
Right.
and then you use /64, and your lower 64 bits are essentially guaranteed to be unique throughout the entire internet.
Yeah, the question is so yeah, is that the...
Well, that's the way I understood it when I was reading, IPv6 Pro.
Utima? Yeah.
I was reading his book, and the impression I got was that when a customer signs up with an ISP, you give them /64, you now have 64 bits of play with.
I guess if the NLA, the question was if I have a TLA and an NLA and a format prefixer and each ISP is given 64 bits, do I have 64 bits that I can play around with? Or if they give me an address, will that be unique? Yes, it'll probably be unique if they use global-based addressing, but it depends on whether like a university who's given a TLA and an NLA may say, okay, the computer science department has this site-level aggregator, and they only need, 1 million machines, so, we'll only give them this many bits, but the biology department may need half of that, so we'll give them a bigger SLA. It depends on how they put the SLA in there. The EUI, the interface on the end, the 64 bits, the 64 bits on the end will be unique because it's based off of your MAC address. but it depends on how they, yeah, that's right, because the SLA is in the first 64 bits, so it depends on how the ISP gives it out. Yeah, I got, let me just finish one more slides here, and then I'll take questions for the rest of the time. So, you know, tools need to be ported. And there's a great, Stevens came out with the next Unix network programming book, and he covers IPv6. How do we program IPv6? BOV6. The netcat, Bovis, yeah, the bovine, yeah. So, yeah, I'll have to write Dill and say, yo, Dill, man, why are you bringing out BOV6? Because there's not, you know, right now it's so, in such an infancy stage, there's plenty of opportunity out there to play. And there are probably still, there's tons of security flaws out there, I'm sure. They're just getting, you know, they're just kind of getting rolling. And I just kind of rambled for a few guesses here, and I put some question marks, renumbering, how do you make sure you're renumbering from a correct source? If I go from there to here, how do you prevent routers from doing this? How do you prevent machines? Because now I can renumber and say, if I'm in a new network, go, oh, well, yeah, you know, I am the router right now. You can send everything through me, and have a big black hole. You know, people have set Windows boxes up wrong in labs that I've been at, and then all of a sudden, you know, where it just kind of comes to them, and everything gets routed to them, and it doesn't know what to do with it, and it just drops everything. You know, mobility, the ability to say, or in a mobile ad hoc network, here, I'm the new router for this room. I can route everything out because I have a connection out the wall, so just send everything to me. And there's, you know, you got to have security for some of these things, and they'll come around. But things need to be ported, tools need to be out there. Anything that's for IPv4 will be for IPv6, and so there's plenty of stuff out there to do. Yeah, go ahead. So this is where I'll take questions right now. Before I take questions, here's the RFCs for IPv6. That Bellevin paper I referenced, Bradner's book, and was developed in '96, kind of told like the theory, like why we did this. He took the IETF minutes and said, well, why did we decide 128 bits? And why did we do this? That's a good book. It's different essays. The Deering Internet, that's the base IPv6 protocol. That's the Hutima book we were talking about, IPv6. A paper I ripped a lot of the slides off of, and Richard Stevens at Network Programming Books. The notes, I guess I'll give them the DT or something like that, but we'll see how it goes. So I guess from now, I've been talking for 50 minutes, so until they kick me out, yeah. Sites with references. IETF.org will have those refs off of there. The books and the papers, I guess, look them up in the library. Sixbone. Some of the sites are listed in some of those papers and books. So I go to this, like the Lee paper, and Hutima probably has some sites in there that you could go play around with, and probably download it and install it and get a test address and put yourself on IPv6 and, you know, get a million addresses to yourself. Yeah. Let's go with that in the back over there. The question is, how do we deal with multi-homing? Because if we put more than, the question was, if I have multi-homed hosts, which are different, basically gateways, anything that has more than one, I still got to advertise all of these. Is that right? How's the deal with this? That's the question. Probably based, I guess it would be based off those prefixes like it was down there. I mean, you still have to do that, but in order for go to 3 or 4, that slide back yonder. Hold on. All right, so I'm from the south, all right? Yeah. I guess right here, if you had different, this would be the ways that things were up, and if my machine both had prefix 3 and prefix 4, I guess it would go to the nearest one. I'm not really sure how that would, I guess it would be done off of the variable length subnet masks.
From what I see, it looks like you would, just like you do today, where you advertise
not really sure. Anycast? Well, Anycast actually does an expanding ring search, and they talk about that in the Lee's paper, where you just sit there and try to find out where it goes, and eventually you'll find something. Well, now, that's not like the nearest, nearest is in hops, so it may not be nearest as in geographic, but... As far as broken links going down, yeah, there's stuff that can be done with that, but...
IPv4, because we've been playing with it so long, exploits, let's say, reach day. It's not all exploits are. We're starting all over again with IPv6. When Microsoft's going to implement this, it's probably going to stop. And there are going to be a lot of exploits in the beginning. Most of all, they didn't think of that.
Yeah.
There's a new attack there. I think I'm telling you, that's one of our impacts with a new protocol being implemented across multiple platforms.
I'll say in a second. Hold on. Okay, if anybody wants a question, I'll be outside. They just said we only have this room till 1 and they've got to set up for something else, so I'll meet you outside.
Thank you.